Alright, so last time we were discussing the integral test, and the integral test is used to determine whether a series converges or diverges as one of the different tests that we're going to cover. However, recall that we cannot just integrate any function even though it looks integrable. There are three conditions that have to be met. Number one, the function that represents the sequence has to be continuous on the interval of integration, and that interval of integration, it's the same as the interval that is comprised by the series. For example, we can also have another series from n equals to 4 to infinity. So we have to integrate from 4 to infinity, and we need to make sure that the given function is integrable is continuous on the interval for infinity. Also, we need to make sure that the function is positive and on the interval. And most importantly, we need to make sure that it is a decreasing function, because if it's an increasing function, the values get bigger and bigger and bigger. What's going to happen there?
Reach infinity.
It's going to reach infinity, and what does that mean in terms of talking about the series? It's going to diverge, right? So we're going to get infinite values. So why? All right. So we did a couple of examples last time. Let's look at the third example. So we have ln of n on the interval 2 to infinity. Okay. So number one, let's see. So letter A, rather, continuous. So the discontinuities for ln of n over n, number one is 0 for both the numerator and denominator. However, that discontinuity is not part of the interval 2 to infinity. All right, so we're just looking at the interval 2 to infinity, excluding that 0, which is a discontinuity. So we're good. We're good here. Letter B. So for letter B, is this positive? Yes, it's positive. Think of every possible input on the interval 2 to infinity. The output, regardless, it's always going to be a positive value. All right, and letter C, the tricky one, might be a little bit tricky. So that's decreasing. Okay, so we need to set the corresponding function f of x ln of x over x, and then we need to do the calculus for this function, take the derivative to find the values of the slope, and well, you'll see how this is going to work. So f of x, or rather f prime, so in this case we will need to use the quotient rule. So recall the quotient rule. So whenever you have u over v prime, that's u prime v minus v prime u over v squared. Right? That is the derivative of the numerator times the denominator without differentiating, minus the derivative of the denominator times the numerator without differentiating, and the whole thing divided by the denominator squared. So let's take the derivative. The derivative of ln x, which is 1 over x, times the denominator, which is x, minus the derivative of the denominator, which is x, and the derivative is 1 times the numerator ln of x. Okay? And divide by the denominator squared, and let's simplify this. Number one, see how these x's cancel. And f prime of x equals 1 minus ln of x over x squared. Alright, at first glance, this derivative looks like positive, isn't it? Well, but number one, think of very, very large values of x. I mean, think of ln x, ln of a really, really big number. I mean, not even that big. For example, ln, for example, of b squared. Isn't this 2? But what's 1 minus 2? Negative 1. And that's actually the lowest bound in the series that we're working with, right? 2. So from that interval and on, all the values are negative. Now, if you want to represent this, or to justify this in a more generalized way, check this out. Factor out the negative and reverse the order of the terms in the numerator. And I think this is more clear that the derivative is negative, isn't it? So in this case, we got a good argument to justify that the given function is decreasing. So we're good to go. Let's set up the integral, the improper integral that we will use to determine the convergence of the given series. All right, so the integral from 2 to infinity of ln x over x with respect to x. Well, in this case, let's see, any ideas on how to set up, how to evaluate this integral? Yes?
U can be ln of x.
U can be ln of x, so I use substitution. But before doing the u substitution, which is correct, we need to set this as a limit problem. So that's the integral from 2 to b, ln of x over x, and let's do the u sub. U equals ln x, du equals 1 over x dx. And well, let's not change the limit. I don't think I didn't change the limits. I'm gonna leave it like this. So limit of the integral of du, or rather u du, and then that's limit of u squared over 2, b approaching infinity, and evaluated. Well, not yet. Limit ln x over 2, evaluated from 2 to b rather, as b approaches infinity. And well, what's going to happen? Well, number one, let's use the fundamental theorem of calculus. Upper limit minus lower limit. I'm going to take out the 1/2, these two in the denominator as a 1/2 to make this a lot more simple. So ln of b, oh, I forgot the square here, quantity squared, minus ln of 2, quantity squared. Well, let's just think of the first term. What's ln of b as b approaches infinity? Infinity. On top of that, square it, even more infinity. Minus ln of 2 squared, well, that's not going to do any harm. So infinity, and our conclusion then is the integral diverges, therefore the series diverges. All right. So that's one more example on the integral test. All right, so let's look, yes?
So for the test, when we get these tests by integrals, we also have to write out the sentence like the integral diverges?
Yes. So for the next topic, the p-series, and you might remember we'll look a little bit at p-integrals to determine whether the integral converges or diverges by just looking at the function of the form 1 over x to the p power. Well, so what we did that before in order to, in a way, prepare you for this topic, for p-series, and well, the criteria is exactly the same. If you have a p greater than 1, your series converges, but otherwise, if the value of p is less than or equal to 1, diverges. Just that. So let's have a look at these examples. So number one, we have sigma n equals 1 to infinity of 1 over n squared. So all we have to do here is identify the value of p, which is 2. And well, that number 2, is that greater than 1 or less than or equal to 1? Greater than 1. Alright? This means converges. Converges by p series test. I think it takes longer to write down the conclusion rather than yes. Alright, let's look at another example. Okay, so yes, radicals are very common when it comes to this kind of series. 1 over the square root of n. Well, that doesn't look yet like 1 over n to the p, but of course we know we can incorporate the properties of radicals and rewrite the series in the form. So sigma n equals 1 to infinity 1 over n to the 1/2, and in this case all we have to do is judge that value of p, which is 1/2. Is that greater than 1? Is less than or equal to 1, which means diverges by p series all right. Sigma n equals 2 to infinity of n to the negative 1. Okay, so we don't have it in the form of a ratio. Let's just rewrite it. N equals 2 to infinity 1 over n to the 1.001. All right. These decimals right here are going to make a whole difference, because the value of p, which is 1.001, is that greater than 1 or less than or equal to 1? Greater, right? I mean, by just a thousandth, that's all it is. That makes a whole difference. So converges by p series test. Letter D.